Okay, our next speaker today is Jorge Lira from Universidade Federal do Ceará, and his talk is on height and gradient estimates for graphs with constant mean curvature.
Thank you, Kate. I'd like to thank the organizers for this possibility, this nice possibility of giving a talk, this colloquium. And the subject of this talk is to show some a priori estimates for the height and gradient of graphs with constant mean curvature in some kind of property spaces. So the geometric scenario for these graphs is some Riemannian manifold, a Riemannian manifold. When you have a Killing vector field, and for simplicity, I assume that the distribution associated to y, this distribution which is orthogonal to y at each point, is orthogonal, is integrable. And in this case, I'll take an integral leaf, a complete integral leaf of this distribution. In this way, I'll denote by this capital theta the flow generated by y. I suppose that these flow lines are complete. It's not an essential hypothesis, but just for making the statements briefer. And I will consider, finally, a domain, not necessarily bounded domain, just a domain with a smooth boundary, regular boundary, in this integral leaf P. And given a function, a real function defined on omega, the Killing graph of U is the hypersurface obtained by moving a point x in omega, take a point x in omega, move this point along the flow line of the flow generated by y by this amount, U of x. So we have this picture, omega, P, this omega, and for each point, move this point along the flow line of y by this quantity, U of x, and making this for every point on omega, you get the Killing graph of this function u over omega. So this generalizes, for example, this kind of space when you have a warped product. You have here a kind of warped product structure. This gamma is annotation for a shorthand for this, for the squared, the inverse of the squared norm of y. So, in fact, the ambient space has this warped structure in terms of this gamma function, and obviously this includes the case of Riemannian products and space forms. So space forms, graphs in space, into space forms and into Riemannian products are special cases of this very general notion of Killing graphs in these warped spaces, in these warped products. And the induced metric in sigma is a perturbation of the metric in P given by this first order contribution, which involves this quantity times the differential of u. And the orientation along this graph is given by n. So the expression for this n is that one, where w, you appear quite often in this talk. W is the infinitesimal volume element on the graph. This gradient is taken on P, on the leaf P, but is transported along the flow lines of Y in a geometrical way. So I just identify the gradient here with his parallel copy at some point along the same flow line through a point X. So in terms of this normal vector field, I can compute the mean curvature of this graph. And the mean curvature of this graph is related to, as expected, to some variational problem. You just consider, for example, the volume functional, and you have take, for example, a relatively compact subdomain D on omega, and then you can take variations of the volume of the graph over this compact region. The expression of this volume is this. This is the Riemannian volume in P, this one. So this is the Jacobian for calculating, computing the volume element of the graph. And now you add to this a Lagrange multiplier given by this. So this is a function h, a function which depends only on the points on the leaf. It's independent of the parameter of the flow. And this is the arc length of the flow lines of the flow generated by Y. So if I take critical points of these constrained functional, you have the Euler-Lagrange equation, which is written in terms of the function u as this. So this is the mean curvature equation of a Killing graph. And this Lagrange multiplier here is exactly the mean curvature of the graph given in terms of these differential operators. This divergence operator and this gradient are taken with respect to the metric sigma into this manifold P. So another way to write this equation is to consider a weighted divergence operator. So I take this first order part into this modified operator, and the definition of this weighted divergence is the usual one, up to a sign. And the weight you consider here is the square root, is the log of the square root of this gamma function here. So this is the particular choice of weight in order to associate to this equation a weighted divergence. And this is the main theme of the research you are doing, is to relate the PD associated to the mean curvature equation of graphs with this kind of weighted divergence operators. So you want to explore this simple relationship between both equations. And for example, if you take the Stokes theorem for this relation, you get a nice observation. It's simple, but a nice observation due to Salavesa in this more general setting, that the mean curvature of the Killing graphs has an upper bound, a natural upper bound, in terms of for each relatively compact subdomain D inside omega, you get this upper bound to the mean curvature of the graph. So this is a kind of weighted Shiger's constant associated to this particular geometry, this particular open space. So for example, if you explore this relation in terms of some special ambient space, for example, if you consider rotationally invariant matrix in M, so take on the leaf P, take a pole, so P is a model space, in the sense that you have a set of global Gaussian coordinates on P. This is the metric, the standard metric in the Euclidean sphere. And for having the ambient metric, just add here a radial function when this rho is the norm of y, which depends on r. And this coordinate r, which is the radial coordinate, r is the distance on P from O to x. So for this particular choice of ambient space, this upper bound means that you have natural examples for CMC Killing graphs, choosing Rho Xi in a nice way, in some sense. You have two kinds of examples. You can produce graphs which reaches this flow line through O orthogonally, but have some infinite slope at finite radius. So this corresponds to CMC spheres. And the quantity which is in the quantity is in this right-hand side has to do with the flux of the surface when you cut the surface on along leaves of the foliation associated to y, and the flux becomes zero at this highest point. So you have this, and in some cases, for example, if you have Hn cross r, and as a natural example of this, you can produce these solutions, but with a slope coming to infinite just along the asymptotic boundary of the space, not in the region, in a finite region of the space, but asymptotically, like this. And in this case, you have CMC disks. And this kind of barriers, this kind of hypersurfaces with CMC, with constant mean curvature, may be used to produce, to obtain high estimates for graphs over compact domains, in the sense that if you have for example, omega compact, you can omega compact inside some normal ball centered at O. You can use this kind of graph in order to estimate the height of an arbitrary Killing graph defined over this compact domain. This is just a way of using elementary maximum principle to get height estimate. Just moves this particular graph along the flow lines and get the first contact point, and you have a trivial height estimate. So the idea is to extrapolate this construction for the case when the metric is no longer rotationally symmetric, so have again a general Wapert product. This is one of the problems. The other one is to extend this kind of height estimate or gradient estimate for unbounded domains. So you need to produce a version of the maximum principle for unbounded domains. This is the purpose of our work. How to extend this kind of configuration to general metrics and to possibly unbounded domains instead of these compact ones. For compact domains, for example, it's not a hard task because you just mimic the proof of the height estimates by James Serring, or as is presented in the textbook by Gilbert Rüdiger. There is an easy way to produce height estimates for the compact, for general compact domains. It's not really hard to obtain height estimates because you can use barriers which depends on the distance to the boundary of the domain. Sorry, the boundary is here, the boundary of the domain. So you choose barriers depending only on the distance to the boundary. So, for example, if you have graphs with 0 boundary values, just take here some function, some real function of the distance, not to a point, but to the boundary of the domain. And in the sense of these Wapert products, if you take this omega and the boundary of omega, this is the cylinder, the cylinder over this boundary. So the distance measured here is the same distance measured there. So the distance is preserved along the flow line. So in some sense, this is the same of the distance to this point y related to x to the boundary of k. So if you insert this choice, this particular choice of function into the mean curvature operator, the principal part of this gives the mean curvature of this cylinder. Because it appears when you calculate the principal part of the operator, it appears here the Hessian, basically the Hessian of the distance. And the Hessian of the distance gives the mean curvature of a parallel cylinder at distance d, at a fixed distance d. So in order to get a super solution or a sub-solution for the mean curvature equation in terms of this kind of barrier, you have to compare the mean curvature of the cylinder with the mean curvature of the graph. Then about this kind of procedure, the main existence result for compact domains is due to Deitze in a collaboration with Hinojosa. The two main assumptions for guaranteeing the existence of graphs over compact domains is that the mean curvature of the graph is less than or equal to the mean curvature of the cylinder K over the boundary of the domain. But if you look at the calculations carefully, you see that the mean curvature which appears there is the mean curvature of the cylinder at level D. So I have to compare this mean curvature with that one. So in order to have this comparison through a Riccati type equation, the hypothesis you need is that the Ricci tensor of the leaf P is bounded by something like this. Maybe the mean curvature of the cylinder. So this is the assumption needed to have the correct sign in the Riccati's equation. So this assumption guarantees that this mean curvature is greater than or equal to the original one, and then you can compare these two mean curvatures in order to get a barrier like that. So this is the way for having height estimates and gradient estimates along the boundary of the domain. So working with some general procedure about interior estimates, you are able to get height estimates, boundary gradient estimates, and interior estimates. And using this and the continuity method, you can guarantee the existence of a Killing graph with mean curvature, age, and arbitrary boundary data, say phi. Just perturb age and phi to 0, and then begin with the continuity method, getting compactness at each step, due to the fact that you have a uniform height and gradient estimates for this case. But now you address the problem of uniqueness or non-existence of graphs like that for unbounded domains. So the first result towards this is this goal is the following one. Now you consider domains not necessarily bounded. So the first result is a joint work with Alfonso Romero, da Universidade de Granada, e Rafael Rubio, da Universidade de Córdoba. And the result is that if you suppose that the leaf P, the integral leaf P, with the original metric, the original Riemannian metric sigma, if you suppose that this is a parabolic Riemannian manifold, and if you assume that the function gamma, let's recall that gamma is this, but this is a function defined on P because the length of the vector field do not change along the flow line. So this is basically a function on P, So you assume that the infimum of gamma on P is greater than 0, so the norm of gamma is bounded for above. And if you have the Hessian of the weight function, if the Hessian of the weight function is non-positive, this is the way of using this kind of operator to study graphs over unbounded domains. So you have to impose some condition of the weight on the weight function. So assuming that, then the only bounded entire minimal Killing graphs satisfying this upper bound for the gradient for some positive constant C are the leaves, say P times some C, small c here, some leaf of the foliation associated to I. This hypothesis here is somewhat restrictive, but it's needed in order to guarantee that the weighted operator which appears in this context the linearized operator with this particular weight here. This operator is, has some parabolicity condition. So this is the main tool for proving that if P is parabolic, the graph itself is parabolic. So it's a kind of assumption for transplanting the parabolicity condition for the leaf to the graph. And the idea is just to use two equations which correspond to this PD, but written in some intrinsic way. So the first intrinsic equation, so we take here the Laplace operator in the graph, not in the leaf. The first equation which appears here is that one. And this quantity here is particularly important because y times n is 1 over w, so this is basically the inverse of the norm of the gradient, basically. So this is the first equation, and the second equation you use for obtaining this kind of result. The second equation is just the Jacob's equation, because since y is a Killing vector field restricted to the graph, this gives a Jacob function. So this is in the case when the graph has constant mean curvature. This is the well-known equation of the second variation of the volume of the graph. When you take variations along this vector field, and combining these two equations, you can, using parabolicity of the graph, get this result. Other version of this kind of result also in joint work with Romero and Rubio is under the same assumption, P is parabolic. P is parabolic, but now you assume that the infimum remains bounded from below. The gamma is uniformly bounded from below, but now the weighted Hessian is now comparable with the metric, and the weighted Laplacian, this is on P, the weighted Laplacian of the weight function for some constant for some positive constant C. Assume these conditions, these assumptions. Then again, the same conclusion holds the entire minimal graphs, but now you just assume that they are bounded from above, from below. By symmetry is the same if you change signs from below, and satisfying this bound on the gradient. The only entire minimal graphs like this are the leaves. The same conclusion. So the problem seems to be to obtain gradient estimates in both results. So if you are able to get this using other machinery, you get a kind of uniqueness result for unbounded graphs. In this case, graphs over the entire leaf P. And you can wonder about the existence of metrics satisfying this, but you just use the Hessian comparison theorem, and if you have some control on the radial sectional curvatures of P, you are able to get more geometric conditions, assuring that you can find weights satisfying this kind of assumption. So this is not a problem. The real problem is about to get either gradient estimates or the parabolicity of the graph without using gradient estimates, or the criterion for parabolicity of the graph in direct way without using this assumption. So about the first issue, about obtain gradient estimates, let me just mention other result assuring the possibility of having these gradient estimates. This is a more recent result with Markus Neitzer, and in this case, you have always this same kind of open product. Just recall that rho is the norm of y, which is the same as the inverse of the square root of gamma in our notation. So I have this manifold, this warped product, and you assume now that the ambient Ricci tensor is bounded from below for some positive constant L, or you assume that the Hessian of rho is bounded. It's the same. I mean, you can use this instead of this. And assume that you have some control of the radial sectional curvatures of P measured along radial geodesics issuing from this point O. So these are bounded by some nice function here, G, even a smooth function on the real line. So D is, again, this distance, this geodesic distance on P. And I can put here constant if you want. And you have an extra, no, that's all I need. So if U positive describes a CMC Killing graph over some geodesic ball on P. Let me put this here. In this case, then the gradient on P of the function U, not the same gradient as before, because this is the gradient on the graph, on the submanifold sigma. So the gradient at this point is bounded by a quantity like this, and this, well, it's somewhat hard to write these equations, that is this constant, but for example, D is something like the log of this guy, and this K is related to some constants which depends on the something like this, which is nice, but depends also on the geodesic curvatures of the flow lines, and also on the mean curvature of the graph. So you can track this, keep track of these constants, and see that these constants depends on the radius in a nice way, because the interest is to take the limit when r goes to infinity, so to obtain a sort of global gradient estimates when this radius goes to infinity. So this is quite well behaved for doing this, but the problem is about these two terms here. For example, the same approach was made by in a joint paper in joint work by Rosenberg, Schutz, and Spruck. And in their case, they have no this term because you are in the product space, so this is 0, and they are working on minimal graphs in this remaining product. So this term drops of the constant, and I will get a nice estimate even if you consider minimal graphs in remaining products in a half space above some leaf. In our case, because you have these two extra terms, you just have a kind of a uniqueness result for graphs into a slab. So the main consequence of this kind of estimate is to obtain a sort of uniqueness result. And the statement of this is so assume that instead of this more general assumption, just assume that the sectional curvatures of P are bounded from below for some non-negative constant. Assume that the Ricci tensor of P is non-negative, which is a limit, it's a sort of limit of this kind of condition for the bounded graphs. And also assume that the ambient Ricci tensor is bounded by some constant, or that the Hessian of rho is bounded. Then, if the norm of the vector field Y is bounded from below, so we have no singularities for this vector field in an asymptotic way, and if the gradient of the norm is bounded, then an entire bounded means between two leaves in a slab, CMC graph, killing graph, is minimal and must be a leaf. So in the case of Rosenberg, Schutz, and Spruck theorem, they have assumptions about these two curvatures. They are working in the product space, not an open product, so you have no conditions about this. The rho is equal to 1 everywhere. And they got the same result, a similar result, but for minimal graphs in a half space of the space of the P cross R. The techniques for obtain this estimate, because this estimate is the key tool for having the uniqueness result. The main technique here is due to Coreva, so I tried to use this nice estimate by Coreva for adapting it for this more general geometric ambient, and the consequence of these estimates, this gradient estimate, is this result. One of the consequences of that. So maybe it's possible to refine, to look very carefully at these constants and to have more general results, and to compare not with leaves, but with more general graphs. And this is a result that I want to show you in the sequence. How many time? 10 minutes? Okay. So the last two results I want to show you are based on a weak maximum principle at infinite for these graphs. In fact, for proving this, you have to use the generalized Morial maximum principle for guarantee that if you start with a CMC graph, in fact, this graph is minimal. So first to use this maximum principle at the infinite for reduce constant mean curvature in general to mean curvature equal to 0. The second step was to prove that since you have gradient estimates, a global gradient estimate, due to this kind of expression here, you can make this estimate global. Since you have this global gradient estimate, the graph, the height function on the graph solves a kind of harmonic function equation. Okay? And using a Liouville type theorem due to Saloff-Costa, as Rosenberg, Schutz, and Spook did, you can guarantee that the minimal graph is in fact a leaf. So you have these two components on the proof. And according to the fact that I have to use the weak maximum principle, the idea now is to extend this maximum principle at infinite for the case of general CMC killing graphs. And this was done very recently in a joint work with Luis Alias and Marco Rigoli. And a first consequence of this result on the generalized maximum principle for killing graphs is the following one. So it's a theorem in a joint work with Luis Alias and Marco Rigoli from Murcia and from Milan. And now the assumptions are, suppose that the infimum, the assumption is in the opposite sense. The norm is bounded from above, and then you have, instead of some condition on the gradient, you have some control on the volume. So you have the log. So if the weighted volume is comparable with this power, in this sense, where this sigma is some constant between 0 and 2, strictly less than 2, then if you have this control on the weighted volume of the leaf and on the behavior of the vector field, this is no longer assumption about the graph, but about the geometry of the leaf, the weighted geometry of the leaf. So in this case, then n CMC killing graph lying between the graphs. So you have two spatial graphs here, a barrier from above, a barrier from below. They have the same form depending on the distance to a reference point here. So this is now R of x. This to the same power as here. If you have this outside a compact in P, so this holds outside a compact, of course. And if you have the graph trapped into this region, which could be more general than two slices as before, then such a graph is minimal. And using the estimates, the gradient estimates you obtained with Deitzer, is sigma is 0 and P is non-negatively Ricci covered, then the graph must be a leaf. This is a kind of conclusion using the generalized maximum principle. You refer to that. So just for finishing, asking the second question about parabolicity. In a joint work with, in the same joint work with Elias and Rigoli, you obtained a criterion, the final result, criterion for the parabolicity, because in the result with Homer and Rubio, you have to impose the gradient bound assumption. So now we have a direct control on the parabolicity of the graph, just assuming that I'll state in very rough terms because I have no time enough. So the condition is that if you get the weight which appears in the equation, and you take these integrals on the geodesic boundary, geodesic spheres on the leaf, this to some power. If this is not integrable, then the graph is parabolic in the sense of the linearized the mean curvature operator, and then are able to conclude that the graph again, if it's CMC, should be unsliced. So this is just an indication that you can replace the assumptions about gradient estimates for assumptions about the weighted volume of the leaf, like this and this. So that's all. Thank you very much for your attention.